Alrighty, let's start taking a look at these. So what we're asked to do here is we're asked to evaluate. We might be able to do these just by themselves. We might need to use change of base formula. We might switch things around in the exponential form. So we have a lot of options when it comes to how to solve these or evaluate them. We're looking to get our decimal answers here. That means we may or may not need a calculator. Probably will. So we can do that with the change of base. We can get them decimally. Our first one we're asked to do is log of 45. How can I get log of 45 over log of 10? Yeah, you can do it using change of base where you do log of 45 over log of 10. This is common log does it kind of the hard way. Because I can just straight up type of log of 45 in the calculator. If we want to do this change of base style, since this does have a base of 10 here, here's not doing the weird zoom in thing. You can absolutely do this as log 45 over log 10. Totally works. It's going to do the exact same thing because common log of 10 is just 1. So you can just straight up type this in the calculator as it is, since common log is a button on our calculator. So log of 45 has what value? 1.65. And I do we said 10,000, so we're going to go 4 decimal places. 6532. Because that's tenths, hundredths, thousandths, 10,000ths. Counts by, yeah, so 10,000ths is 4. What about log base 4 of 256? I think, yeah, it should be 4. Like, we're not going to get a decimal answer because what this is our base of 4 to some power equals 256. And 4 to the 4th gives you 256. So you don't have to do this one with change of base. This is a power. 256 is a multiple of 4. But you can also do this change of base doing our log of 256 over log of 4. It'll give you the same piece. And that's okay. The calculator still gave you that answer. So even if we don't notice it, the calculator can still help us with that. It's just one of those things we don't have to use this every time. We can. It'll work. But sometimes it's making things more complicated than they need to be. The next one, we definitely do need to have our change of base because 15 is not any kind of power of 2. So we can do this exactly the way we did up here, where we're going to take our log of our argument, 15, over the log of our base. Log of 15 over log of 2, and we're going to type that in the calculator. You could do ln if you wanted to for both of them if you wanted to, but you have to do both.
3.9069.
3 equals 3.9069. Because it was 8, 9, and it rounds up. And our last one, log base 6 of 2. What do we get from that one? Yeah, it should be very, very small. Very, very small. Because this is saying 6 to the power of 0.3869 would equal 2. So 6 to that power should be pretty darn close to 2. Okay, so this is using that change of base formula from yesterday down on these bottom 2. Questions on that bit? Okay. Because what we're going to do is we're going to do a little bit more solving stuff today. Got a couple of different types that we need to see. So we're gonna be on page 11. Yeah, this is page 11. Page 11 in our packet. So we've got here numbers 3 and 4. So 3 has a couple of ways I can see us doing it, and so we will kind of see what the vibe is here in just a second. What should we do first for number 3? Taking a look at it. What's our instinct thoughts first? Say it louder. Subtract the 1. Yeah, let's look to get that piece that's exponential all by itself, because we want to be able to get to what p is. So I'm going to subtract 1 from both sides. That's going to give us our 16 to the power of minus 5p equals 4. The heck can we do here? We can put it in log form, absolutely valid. We have a base, a power, and an argument. So we can switch this into log form. So when we do that, we're going to get our log with base 16, argument 4, and it had power of negative 5p. What could we do next? Try to figure out what p is.
Divide -5.
We can divide both sides by -5. Absolutely valid. That's going to give us our log base 16 of 4 all over -5 equals p. So that is all well and good. That technically counts as an answer. I've got a p equals. But if I want to know how many pineapples that is, I got no darn clue. How do we get a decimally answer here? Mm-hmm. Yep.
Change base thingy.
Yep. We need to run this guy through our change of base, because I can't type log base 16 of 4 into the calculator. So what is this going to look like when we type it in the calculator?
Log 4 over log 16 over -5.
You can absolutely do that. Just be really, really careful when we do it. If you do one of these stacked fractions like this. We can also notice that if we have log 4 over log 16, that puts our log 16 in the same spot as this -5. So we could just put it in as -5 log 16, because it moves that base down into the same denominator. So what are we going to get as a decimally answer?
It gave me -1/10.
-1/10 is correct. So RP is -1/10. And if you wanted to, you could come up here and type this in. 16 to the power of -5 times -1/10 plus 1. You could put that in up here to check it, and it would totally work. And since we got a nice tidy answer, it would actually wind up exactly right, not decimally close right. So we use our change of base, we use our logs to be able to figure out what this exponent value is. That's kind of the whole point of logs. There is another way through this one if if you guys absolutely hate logs, you could come in here and think about last chapter, how we could make the bases the same and do it as 4 and 4 squared, 2 times minus 50. Like, you can do it that way. Totally works on this one because we have a multiple. It doesn't often work that way, but it's one of those things. There's multiple ways through some of these problems. Questions on that one, though? All right, let's do number 4, one right next to it. Very, very similar vibe. Super similar vibe. What we have is a very similar process. Is we have 11 to the n plus 6 minus 9 equals 47. What should we do first? Add 9 to both sides. That is going to give me my 11 to the n plus 6 equals 47 plus 9 is 56. What do we do next? Put it in log form. What's that going to be? Log. Yeah, our bases are 11. Our argument is the 56. And it's going to equal n plus 6. That was our power. What should we do next?
Subtract 6.
Yep. It's going to give us log base 11 of 56 minus 6 equals n. Can I subtract the 6 from 56 and have it be log base 11 of 50?
No.
No, I cannot. Remember, logs are very much related to exponentials. They are, in fact, the inverse operations. So order of operations wise, it goes with the E in PEMDAS, not the S in PEMDAS. So we have to do this bit before we can do any subtraction. So this guy is separate from our subtraction. Just like this guy was separate from our argument over here of 4. I couldn't take this and have it be log base 16 of 4 negative fifths. We have to do the log before we can do anything else. So what is this going to look like when we go to type this in the calculator? How are we going to get a decimal answer here?
Log 56 over log of 11. And then out of the fraction minus 6.
And then out of the fraction minus 6. You can type it in just like this. You can also, if it hurts you to have to think about this order of operations, you could switch it here to be change of base and then subtract your 6, and that would make it so you don't have to think it quite as hard. But it's also totally fine to wait till the end to do your change of base. Totally fine. So we're going to get a decimally answer of what for our n? Two decimal places is fine. 4.32. Just because I didn't tell you. So we have our exact answer and we have our decimal approximation. Because log 56 over log 11 minus 6 is our exact answer. This would also count as an exact answer, our log base 11 of 56 minus 6. Totally fine. Log base 11 of 50 is not fine. Can we sense what our most common mistake that I see on these are? Okay. Questions on these two? Okay. So what we're going to do, instead of doing those bottom two right there, I actually want to give us a different question to put there, because there's a style of problem that is not actually in the packet that we really need to see. So we're going to do this in the place of those bottom two. So instead of 5 and 6, we're going to do these two. I've numbered them 7 and 8.
They're not in the packet, so you'll have to write them in. But you can put them in the place of 5 and 6. There's nothing wrong with 5 and 6. They're just very, very much like the ones we did up above. They're very, very similar. They're excellent practice, but this is a different style of question because these have variables in 2 different exponents. You can do this the way we have been, where we switch it into exponential form and then solve. We would just have to do that twice, and it gets kind of gross. So we're going to do this slightly differently than just switching it into log form, because it gets kind of nasty. If we have variables in 2 different exponents, so here for number 7, we have 3 to the 2x plus 1 equals 5 to the x. If we have 2 different powers that have 2 different exponents, what we're going to do is we're going to use a log very much like if we were doing our add 2 to both sides, subtract 9 from both sides, that kind of vibe. So we're going to log both sides. Log both sides. What I mean by that is I'm going to straight up put a log in front of both of these pieces. So we're going to write this as log of, change colors, 3 to the 2x plus 1. And I got it here. Log of 5 to the x. So we're logging both sides. Thank you, Darren. So if we have variables in both exponents, we're going to log both sides. Just like if we multiplied both sides by 2, divided both sides by 7, added 6 to both sides, whatever. What that lets us do is it lets us take our exponents and using our expanding properties, bring those powers down as coefficients. It lets us use that part of this to be able to get those pieces out of the exponent. These are going to look particularly gross as we go through them, and that's normal. So just warning you, these look a little nasty. Because what this is going to look like on our next step is we're going to have our power that was the 2x plus 1 with our log of 3, because we brought that power down. And that's going to be equal to that x times our log of 5. Gross. Super gross. Just warning you, it's going to get grosser.
Oh, yay.
Mm-hmm. Because what we want to do is we're trying to get to an x equals here. So what we need to do is I need to get all my x's on one side and the things that don't have x's on the other. I have an x inside of parentheses over here. So what we're going to have to do first is actually do a distribution here. Ew. So we're going to write this as 2x times our, changing colors again, there we go. Log of 3, not base 3, argument 3, there we go, plus our 1 times log of 3 equals our x log of 5. That's not changing. We want to do this to be able to get that x out of this set of parentheses, because I'd really like my x's to get together. I want these x's together. So the next thing I need to do is to get this guy to cross over. I need him over here with my other x. So I'm going to subtract this guy from both sides to get my x's together, because I don't need them. They can be together over there. So we're going to have our 1 log of 3, which we don't need the 1. I'm just going to put log of 3 because I don't want to write the 1. Equals our x log of 5 minus 2x log 3. Well, now I've got my x's on the same side of the equal sign. They're in the middle of a hot mess of stuff, but they're both there. But if they're both there, what we're gonna do is we're gonna factor out an x. Told you, these are gonna look super gross. So I wanted to make sure we got to it. So we're gonna have our log of 3 on this side. And what we're gonna do is we're gonna take an x out of both pieces. We're gonna factor an x out. It's gonna leave us with, if I take an x out of our x log 5, we're left with just the log 5 part. And if I factor an x out of 2x log 3, we're gonna have our 2 log 3. We're just pulling the x out of it. These guys are numbers. They're super gross numbers and decimally awfulness, but they're numbers. It's like if I had pi minus e. Technically numbers, but gross. So log 5 and 2 log 3 are numbers. They're just super decimally gross numbers, and they look weird. But we're almost to the fact of having our x by itself, because I have x times some number. X times a super gross number, but it's x times a number. Just like if it was, say, 2x. If it was 2x, what would we do to get the x by itself? Divide by 2. We would divide the number away. So we're going to divide the super gross decimally number away, because that's all this guy is a super gross decimally number. So what we're going to have is our x over here, and we're going to take our left-hand side, that log of 3, and we're going to divide it by super grossness. Log of 5 minus 2 log 3. Gross. Answer, but gross. This would be our exact answer. As far as if I wanted to know how many days, weeks, months that is, I got no clue. So we're going to type it in the calculator. I'm going to show you how to do it because this is super nasty. Give me the buttons. There we go. Exit. Calculator. All right. So on this one, what we're going to do is we're going to start with a fraction. Please use the fraction button on these. Trying to do it without the fraction button is so gross. So our numerator is our log of 3. It's going to be really, really important that we know how to close those parentheses on this one. Because in our denominator, we have our log of 5, and we got to make sure we close that parentheses there, minus 2 log of 3. Boop. And we get negative 1.87. We're going to round it at 2 decimal places there. So we're going to take this bit. The 9 pushes this up. So our negative 1.87 is our decimal answer. Whoop, wrong bit. So when we have variables on both sides, it gets kind of gross. It's doable, but it's gross. So the next one we have is very, very, very much like it. I should wind up with enough space, but I can always make it bigger if I need to. So we have, for number 8, and again, you have to write this one in, 4 to the x plus 3 and 6 to the 2x. And our very first step is going to be to log both sides so that we can use our expanding and condensing properties. So our first step is going to be to log both sides. So I'm going to have my log of 4 to the x plus 3 equals our log of 6 to the 2x. You can also use ln if you'd prefer, just because it's smaller and it's one less letter to write a gabillion times. It genuinely doesn't matter which one you use. There are kind of other ways to do this, but this is one of those ways that's the most kind of reliable way to do it. I feel like it's doesn't give us too many, well, if this happens, then that, and if this happens, then that. So then we're going to use our properties to bring our powers down. So we're going to have our x plus 3 in front of our log of 4. And that's going to equal our 2x in front of our log of 6. And again, we want to get our x's together so that I can factor that x out. That's the whole point of needing to do that, is we want to be able to factor that x out. So what we're going to need to do is if we have any addition or subtraction, we need to do the distribution bit. So we need to distribute our x plus 3 onto this log 4. So we're going to have our x log of 4 plus 3 log of 4. That equals our 2x log of 6. And these are long and gross. And they just are. It's just one of those things, they just are long and gross. Even other ways of doing this are not less long and gross. It's just more ABC options on if this, then that happens, then this, then that happens. And I like to do one that has the fewest number of like rules to memorize. So then what we're going to do is we're going to gather our x's together on the same side of the equal sign. So I have our x log of 4 plus 3 log of x. So I need to subtract this guy from both sides. So we're going to have our, oh, I need to move that guy over because I have enough space. Our 3 log of 4, and that's equal to our 2x log 6 minus x log 4. Get our x's on the same side of the equal sign. Because again, log 4 is a number, super gross number, but it's a number. Log 6 is a number. It's a super gross number, but it's a number. 3 log 4, it's a number. So since we have x times several numbers on the right, we're going to factor out our x over here. Our left side is still the same. We're still going to have our 3 log x, or 3 log 4. And when we factor out that x, we're left with 2 log 6 minus log 4. And we're almost to our answer right here. They're gross, but they're almost there. Because again, this is now just a number, no variable in it. This is just a number. So we can divide both sides by this super gross number. So we're going to get that our x equals our 3 log 4 over 2 log 6 minus log 4. And we're going to type that in our calculator very, very carefully to try and find our decimal approximation. This is our exact answer. This is the most accurate, but if I want to know what length of time that is, I got nothing off the top of my head.
Put it on the calculator.
Put it in our calculator. And what are we going to get? See if we can type that in.
I got 1.89.
I also got 1.89. So this would be our decimal approximation. So our exact answer and our decimal approximation. This is as gross as they get, is when there's variables in both exponents. This is as gross as they get. They're super gross. This is as bad as they get. Okay, they do not get worse. But I needed us to see one that had variables in both exponents, and there just aren't any in the packet. We didn't notice that until after they were printed. Okay, we're not going to end on that grossness. Let's end on one that's slightly less gross. Let's do, on the next page, I don't know that we'll get to both. We'll at least do one of them. Let's do one for sure, and then we'll see what we're looking at time-wise. Probably we're just going to do one of them. Just because I don't want to take us all the way to the announcements. That's not nice. Ew. So let's look at one up here. Same kind of vibe. We're solving this. So what should we do first? I only have a variable in one exponent, so we like that better.
Add 12.
Add 12 to both sides. So let's go with add 12, add 12. So that's going to give me e to the 3x plus 2. Oh, sorry, I didn't tell you guys. This is number 1 on the very next page. This is page 12. You don't have to write this one.
Is E as in Euler?
E as in E.
Euler's number or just E?
Same thing. Not variable E. E is a number.
Okay.
Like pi.
Okay.
Yes, that is the Euler's number E. That is the number E. Same doodad. We will never use the letter E as a variable.
Okay.
And in fact, if you look back at your previous math that you've ever had forever and ever and ever, you've never had E as a variable because it makes our brains itch if we try and do it. What do we do from here? Log form. Switch it to log form. So we have our log. I'm going to write it like this first. You don't have to do this if you don't see it. Our log with base E of our argument 26 equals our power of 3x plus 2. What's another way I can write log base E? ln. We don't need to use change of base on this guy because ln is a button on the calculator. So we have ln of 26, which is a number, a gross number, but it's a number, equals 3x plus 2. We still want to get our x by itself, so what do we do?
Subtract 2.
Subtract 2. So we have ln of 26 minus 2 equals 3x. What do we do next? Divide by 3. So we'll have our x equals ln of 26 minus 2 over 3, which is our exact answer because we've got our x equals. X is by itself. Everything else is on the other side of the equal sign. So that's our exact answer. But if I wanted to know how many that is, I got nothing. So to get our exact answer, our decimal approximation, calculator. ln's a button in the calculator. So, boop. We've got our fraction. And in our numerator, we have our ln of 26. Make sure we close that parentheses because then we need to minus our 2 and then divide by 3. And it'll give us our decimal.
And it says to the nearest thousand.
So, yep, to the nearest thousandths. So
then
that's
we have 0.419.
419, because we're at tenths, hundredths, thousandths. And since it tells us, we're going to follow our instructions here. So 0.419. Okay. I just didn't want to end on one of those super gross ones. This one is way less gross. And it let us practice our ln stuff again. Oh, snap. What? Because I do actually have a functional homework worksheet for you today. Yay! No typos.
No double logs.
There we go. So this has what we did yesterday. So a little bit of change of base, but it's mostly solving. And then 3, 4, sorry, word problem. No idea what we're doing tomorrow. Oh my gosh.
Word problems.
As far as it goes to why the heck we have these super gross things and what, oh my gosh, is the reason. There's totally a reason why we have them. It is not just because mathematicians are cruel and unusual, even though they are both of those things anyway.
Why do you do this stuff?
I know. Well, that's why we gotta do them, is to figure out why they do these to us. Oh my god. Because there are actual practical reasons why we have to have these. This is not one of those things that I go, oh my gosh, we don't have to do this anymore. This doesn't make any sense. So we're gonna work with those tomorrow. Not wrong.
I love it.
But yeah, I'm pretty sure we're doing this tomorrow. We might do a little bit more solving to start. Either today or tomorrow or the next day we will do.
Can I get a pass?
Yeah.
Demon.
Yep. Yes, on this silver shelf about knee high, I have a variety. All right, so you guys have about